Welcome back to the Deep Dive, where we plunge into a stack of information, your articles, your research, your notes, and pull out the most important insights, all to make you the most well-informed person in the room. Today, we're embarking on a really fascinating deep dive. It's into a new piece of research that, well, it just might change how we think about teaching artificial intelligence. It's all about making AI learn more like our own incredibly adaptable brains, and it revolves around this concept called rhythmic sharing.
That's right. For a long time now, AI has been, amazing at tasks. It's been specifically trained for, identifying cats in pictures or translating languages, even mastering really complex games like chess. But despite these incredible feats, there's one fundamental hurdle AI really struggles with, and that's adapting to new, changing situations and learning effectively from sometimes very little new information. That's something living brains do pretty effortlessly, sometimes even from just a single example.
Right. So our mission today is to really get our heads around this new bio-inspired learning idea, this paradigm. We're going to unpack how mimicking the subtle mechanical rhythms of our own neural cells could potentially give AI this incredible new ability, the ability to adapt and learn in real time, maybe even predict the unexpected. Get ready to connect some surprising dots because this could be, well, a really profound shift for AI. Okay, so let's unpack this big problem that AI faces first. If you think about the world around us, it's anything but static, right? We're constantly surrounded by subtle, often unpredictable change. Consider atmospheric chemistry, which is always in flux, or the slow, huge movement of tectonic plates deep beneath the Earth, or even something critical like how a tumor state can subtly shift from benign to malignant over time. These are all perfect examples of what researchers call non-stationary dynamics. Basically, the underlying patterns or contexts are constantly changing. The rules of the game are always subtly evolving.
Precisely. And this inherent dynamism of the real world, that's where traditional machine learning often just hits a wall. Most of these algorithms, they're designed to optimize for tasks within a single fixed context. They're sort of like an athlete who excels on one very specific type of court, but then struggles if you change the surface, or maybe the rules, even slightly. If the context shifts, the AI can become completely disoriented. There's a well-known phenomenon in AI called catastrophic forgetting. Imagine teaching a student to ace one type of math problem, but then they completely forget how to do it when you introduce a slightly different version. Even if the underlying principles are quite similar, it's almost as if their previous knowledge gets completely overwritten.
Catastrophic forgetting. Wow, that sounds like a pretty fundamental roadblock for AI trying to operate in the real world. So how do current AI systems even start to cope with these constantly shifting contexts? Or can they? It sounds a bit like when my phone decides to forget all my Wi-Fi passwords after an update, but probably on a much more serious scale.
Huh. That's actually a good way to think about it. Yeah, you're right. On a much grander scale, it's a huge problem. So to deal with these changing contexts, current AI often needs someone, a human usually, to manually tag the data. You literally have to tell the machine, okay, this chunk of data belongs to context A, and this data belongs to context B. You're essentially giving it these predefined labels, classification tokens they're called, for each situation. Without these external human cues, the machine just can't make sense of the different patterns. It tends to forget old data when it gets new, maybe conflicting information. It just sees a jumble, really, a single undifferentiated flow. What's truly fascinating here, though, is that living organisms' brains don't seem to suffer from this at all. They're incredibly good at sensing subtle, nuanced changes in their environment and adapting their understanding on the fly. They don't need someone to manually tag their experiences. They just figure it out.
Okay, this next part is really where it gets interesting for me because it moves beyond just software, right? So this new learning paradigm isn't just about writing smarter code or, tweaking existing algorithms. It's directly inspired by the actual physical mechanics of neural cells in our brains. You mentioned neurons, the brain's main information processors, and these support cells, astrocytes. How do these physical interactions translate into a new way for AI to learn?
Yes, exactly. The key insight here is that learning might involve biomechanics, the actual mechanics of living systems. Think about it like this. Physically squeezing neuronal synapses, those tiny connections between neurons, can actually strengthen those connections. It improves communication. It's a tangible physical change that enhances function. So this research proposes two main bio-inspired ideas for how this could work in an AI setting. First, they suggest that learning involves rhythmic variations in link strength. So imagine the connections, the links in a neural network not being static, fixed pathways, but slowly oscillating in strength, almost like a subtle, continuous pulse. Picture a light bulb that isn't just on or off, but its brightness is constantly subtly dimming and brightening in a smooth rhythm. Okay, like a pulse. And second, and this is really crucial, learning happens when the phases of these oscillations coordinate. Think of phase as just where each pulse is in its cycle. Are they all peaking at the same time, or are some peaking while others are dimming? Astrocytes, these star-shaped support cells that wrap around literally thousands of synapses in our brains, they have these rhythmic hotspots of biomechanical activity. The researchers propose that these hotspots might be what enables this critical coordination, getting those individual pulses to align or synchronize.
Right, so if the links in the network are oscillating and their phases can change, that means information can flow through different pathways in the network at different times. It's almost like rerouting traffic on a complex highway system. It's dynamic, not static. And this synchronization, that acts as some kind of internal signal.
That's a great analogy, actually. When a different state or context is introduced, like that subtle change in atmospheric chemistry, we talked about the active links in the network quickly adjust their phases. They synchronize with others that are responding to that new context. This rapid, self-organized synchronization then acts as that vital classification token for each state. It's how the network internally labels and understands the changing situation. It recognizes, oh, okay, this is the new pattern, which is something traditional AI needs to be given externally by a human. It's genuinely learning without supervision.
That seems incredibly powerful. It's like building an internal compass for the AI, letting it know which way is north in terms of context. So what kind of dynamic systems can this new approach when you implement it on artificial neural networks? What can it actually sense and predict? What did the researchers test it on?
Well, they put it to the test on several complex systems, and it demonstrated a pretty impressive ability to rapidly sense these dynamic state changes without any prior supervision. They didn't have to tell the AI what to look for. It just figured it out by observing the changes.
Wow.
Yeah. So one example was the Thomas system. This is a classic mathematical model often used to describe chaotic physical processes, and the network successfully detected when a chaotic trajectory suddenly switched to a periodic, more predictable orbit. A key metric they track, called R. It measures the degree of global synchronization of the link phases across the whole network. That R value would immediately settle to a unique equilibrium value for each distinct state. So R literally acts as the system's internal label. It provides that real-time context. It's like the network saying, aha, we've entered a new phase of this system's behavior.
Okay, so R is the label. Got it.
They also tested it on the Mackey glass system. Now, this one is known for having a memory. Its current state depends on its past states, and its internal parameters can change continuously, smoothly. Even with that complexity, the R value successfully mimic the continuous sort of sinusoidal changes in the system's memory parameter. So it showed it can track smooth, ongoing shifts, not just abrupt jumps.
Right, not just on-off switches, but gradual changes too.
Exactly. But this next one I think is particularly compelling. The Lorentz system and warning signs. This is a famous model, often used for atmospheric convection, weather patterns.
Yeah.
And it showed how this system could subtly shift into what's called a transient chaotic state before it suddenly collapses into a dead signal, basically stopping. And the R value in this rhythmic sharing network was able to detect those subtle shifts immediately. It acted as a real-time warning sign for an impending system collapse. Yeah, and this happened even when the visual changes in the system's trajectory, if you just looked at a graph, were barely discernible to the human eye. This capability could be absolutely crucial for anticipating severe long-term consequences in real-world systems. Things like climate change tipping points or maybe even potentially impending earthquakes.
That's truly amazing, like a built-in early warning system, predicting problems before they become obvious. But okay, with something so subtle, how do we make sure these warnings are reliable? Like, are there risks of false positives, or how would you actually validate that in a real-world application?
That's an excellent and really crucial question. The beauty of this approach, potentially, is that the R value provides a continuous and direct measure of the system's internal contextual state. It's not just relying on hitting some fixed threshold. The fact that it seems to settle to a unique, stable value for each recognized state provides a kind of strong internal validation. Now, of course, initial research focuses on demonstrating the capability. Real-world deployment would absolutely involve rigorous testing, establishing confidence intervals, error margins. just like any predictive model. But the key idea is that the system itself is providing the contextual information, which could make it more robust.
Okay, that makes sense. So it's not just passively detecting changes, it's actively using these internal rhythms to understand the current state and anticipate what's coming. How does that prediction part work? Does it track anything else besides this R value?
Right, this raises an important point. The network also tracks another collective property called the mean phase, usually written as A. It's derived from those oscillating links, but it's separate from R. So think of R as the network's internal context label. It tells the AI which situation or state it's in. And A acts more like its memory pointer within that context. It allows it to recall and predict the specific dynamics, the trajectory of that particular state.
Okay. So R identifies the context, like we're in state A, and A helps remember the specific path or behavior within state A.
Exactly. The combination of R and A allows the network to effectively store and recall multiple different dynamic states.
That distinction between R and A really helps clarify it. So it uses these two measures together to predict, not just observe. But what about something completely new, something it hasn't seen before? Can it extrapolate?
Yes. And this, I think, is one of the most astonishing findings in the research. They showed that by freezing the R value for a specific state, basically telling the network, okay, stay in this context, and then manually changing the E value, the network could predict the future dynamics of that specific state, projecting it forward. But even more astonishingly, they could actually steer the system's behavior to unseen states. States the network had never encountered during its training phase. It could extrapolate to entirely new possibilities just by manipulating these internal rhythmic parameters, R and A.
That's really pushing the boundaries of what I thought AI could do. So it can recall what it learned and extrapolate to totally new possibilities.
Exactly. This effectively turns the network into what they call a digital twin. Imagine having a virtual version of a complex real-world system, like, say, a specific patient's unique immune system, or maybe the health trajectory of a vital organ. A twin that can not only predict how it will evolve, but also adapt its predictions in real time as the actual physical system experiences changes, like reacting to a new medication or fighting off an infection. This is something standard neural networks without these internal contextual cues they just can't do. They try to treat all that varying data as a single static event, which leads to confusion and errors. This system learns the rules of change itself, not just static patterns.
Okay, so wrapping this up, what does this all mean for the future of AI and maybe how you, the listener, might interact with it down the line? This research takes inspiration directly from how our own incredibly adaptable brains work, specifically these subtle, rhythmic, physical interactions between our neural cells. And it translates that into a completely new way for AI to learn, potentially revolutionizing how these systems function.
Well, it means we're moving closer, potentially much closer, to creating a truly generalist AI. One that can actually handle the messy, dynamic real world we live in. This isn't just a small marginal improvement. It feels like a leap towards AI that can operate in unpredictable environments, much like our own brains do. Think of an AI that could understand the dynamic interplay of a complex climate system, constantly adapting its predictions in real time as conditions subtly shift, rather than just relying on static, pre-programmed rules. This kind of network can sense subtle contextual changes without human supervision. It can learn these non-stationary dynamics. It avoids that really debilitating problem of catastrophic forgetting. And it might even give us real-time warning signs for impending problems. And crucially, it can learn effectively from limited data and then apply that knowledge to unseen situations. That's a truly significant leap forward.
Yeah, the idea of a digital twin that adapts its predictions as a real-world system changes, acting as this intelligent, real-time mirror. That's genuinely mind-blowing. Imagine if an AI could not just diagnose a disease, but maybe predict a subtle shift in a tumor from benign to malignant before it's visible to us, just by sensing these whispers of change in its internal rhythms. That feels like the truly game-changing aha moment here. The potential applications seem vast: personalized medicine, predicting complex environmental shifts.
It truly is exciting. And while this groundbreaking work focused mainly on systems where the changes were driven by sort of a single parameter, like that one value determining the autonomous system's behavior, the obvious next step is huge. Developing models where different parts of the network could track multiple changing parameters simultaneously. That would make the AI even more sophisticated, capable of handling even greater real-world complexity.
It really makes you stop and think, doesn't it? That some of the most profound breakthroughs in AI might come not just from building bigger, faster computers, but from simply paying closer attention to the incredible machinery of our own brains. This deep dive really reveals how fundamental insights from biology, from the very mechanics of our neural cells, can unlock entirely new capabilities in artificial intelligence. It just makes you wonder, what other incredible secrets does the brain hold that could revolutionize technology and help us understand and navigate our complex world even better?
A truly exciting prospect for the future, indeed.
That's all for this deep dive into rhythmic sharing. Thank you so much for joining us on this journey of discovery. We hope you feel more informed and maybe a little more curious about the incredible potential right there at the intersection of biology and AI. Until next time, keep exploring.